Okay, let's talk about Fresno State Honor Code. First, understand or seek clarification about expectations for academic integrity in this course. And by that we mean no cheating, plagiarism, or inappropriate collaboration. Secondly, don't give or receive unauthorized aid on exams, or other coursework that is used by the instructor as a basis for grading. And of course, we're talking also about your lab work. Don't copy your lab work. Don't ask other people about your lab work. Do the lab work yourself. Take responsibility to monitor academic dishonesty in any form and to report it to the instructor or other appropriate official for action. I want to talk to you about some problem-solving strategies that are a good way for you to set yourself up to succeed in the quantitative aspects of this course, problem solving. First of all, identify what the question is asking for, and note especially the units of the target. What are you looking for, and what are the units of what you're looking for? Make a notation somewhere on the page that that's your target units. Then review the given information and determine the starting point. Again, notice the units of the starting point. Find the conversion factor or factors necessary to cancel the units you don't want and work toward the units that you do want. Look at your answer. Does it make sense? This is an important step that students frequently leave out. You can estimate the rough size of an answer, and if you get an answer that's really off the wall, you should be able to catch it and then correct your work. Don't just rely on your calculator. The answer that you see in the calculator does not necessarily mean you have the right answer. If you've made a mistake, if you've slipped putting in numbers or decimal point, that's going to show up as a wrong answer. Don't put blind faith just because your calculator says that's the answer. Garbage in, garbage out. And always check for significant figures in your answer. Follow the rules in determining significant figures and apply them to all the problems that you end up doing in this course. Now, before we actually start doing chemistry problems, we need to discuss significant figures or significant digits of a measurement. Every measuring device has limits to the precision of its measurements. As an example, we show two measurements of length. The first device shows only integer values of centimeters, while the more precise measure below it shows tenths of centimeters. So I'd like you to pause the playback and see if you can write down the length of the black bar in each case. Go ahead, pause it, and then come back to the video. Okay, let's do this. For the upper one, showing only integers of centimeters, our black bar stops somewhere between 15 and 16 centimeters, doesn't it? Now, it's not quite to the halfway point. It's somewhere a little less than the halfway point. So we could write 15.4 centimeters. Even so, we call this last digit that we're writing in the tens place a guess, really. It's uncertain as to whether it's 4, maybe it's 3. It's what we call an uncertain digit. Now let's go to the more precise measure of length below it. And here we have another black bar, but this measuring device shows tenths of centimeters. Each one of these represents a tenth. So this is 14.1, 14.2, 14.5 over here, 0.6, 0.7, 0.8. So our black bar is somewhere between 14.7 and 14.8 centimeters. Now we can look at the distance between the 0.7 and the 0.8 and again make a guess where that black bar is between 0.7 and 0.8. We see it's a little beyond the halfway point. I would guess, just from looking at that, it's 14.77 centimeters. It could be 14.78 centimeters. Again, the last digit we write is what we call the uncertain digit. So when we take a measurement, the number of digits we write down in the measurement is an indication of the precision of the measuring device. And when we look at a value from a measurement, we need to be able to determine how many significant figures are in that measurement. So let's talk about now the rules for determining which digits are significant. First of all non-zero digits in a measurement are significant. Zeros can be significant, or if they're being used to locate the decimal point, may not and should not be considered significant. So zeros that follow a decimal point and a non-zero digit are always significant. They're not being used to locate the decimal place. So the number 2.10, it has three significant figures or three significant digits because the zero is significant. And zeros between two non-zero digits are also always significant. 2008, that's four significant figures. The zeros are significant. But zeros to the immediate left or right of a decimal point are not significant. 0.021 only has two significant figures, the 2 and the 1. The zeros are not significant. Zeros at the end of a number without a decimal point are not significant, as in the number 200 with no decimal point showing. That's one significant figure. The zeros are not significant. They're being used to locate the decimal point. But the convention we'll use in this class, and this does vary from class to class, it's fairly arbitrary, that if a decimal point is showing, then the zeros at the end of a number are significant. So for example, the number 200 decimal point has three significant figures, and the zeros are considered to be significant. So using these rules on our measured black bars here, we came up with 15.4, with 4 as the uncertain digit. And according to our rules, since we have no zeros, all of these digits are significant. On the lower bar, where we got to the hundredths place as the uncertain decimal place, we have 14.77, and that is 4 significant figures. Now suppose we wanted to find the area of a tabletop with these dimensions. We would multiply length times width, or 15.4 centimeters times 14.77 centimeters. Our calculator returns 227.458, a number with 6 significant figures. We would need to round this answer to 3 significant figures, the smallest number of significant figures of the data leading to that calculated value. When multiplying or dividing data, you round off your answer to the smallest number of significant figures of the parent data. So our area would be expressed as 227 square centimeters. Now when we add or subtract is a different rule. In the second case, the question is how much longer is the top black bar than the bottom, in centimeters and then in millimeters. And of course we're going to subtract them, aren't we? We get 0.63 centimeters. Now, take a look here at the uncertain digits in each one of these. In the 15.4 case, the 10th digit, this 4, is the result of a guess. It is the uncertain digit. And in the lower number, the ending 7 is the result of a guess. It is the uncertain digit. Well, we're going to have to round off our answer to the tenths place here because the tenths place is now contaminated by this uncertain digit of the 15.4. In addition and subtraction, the answer must have the same number of decimal places as there are in the measurement with the fewest decimal places. And in this case, that would be the tenths place. And our answer would be 0.6 centimeters. Now let's start doing some problems. Convert 16.3 liters to gallons. So the first general step that you do is identify the units of your target. And in this problem, it's pretty clear you're trying to find gallons. So I'm going to write just up here in a box gallons, just to remind me that that's my target. It's pretty obvious in this question, but in more complicated questions, you'll be doing well if you identify the target. The target usually is the easiest thing to determine, and it gives you a clear map as to where you're trying to get to. So it's very important to identify those units. As I said, we want to end up with gallons. The starting information is next, and it's pretty clear that we're starting with 16.3 liters. So that's our starting point. Now, here we have a conversion. 3.785 liters equals 1 US gallon. That's an equivalence, isn't it? And as an equivalent, we can write this in one of two ways. We can write it as 3.785 liters in the numerator and 1.000 US gallons in the denominator, or we can write the inverse. Because these two numbers here share the same value in the context of the units that they have. They mean the same thing. The ratios are valid whichever way we want to write them, either with the liters on top and gallons in the denominator or vice versa. Only one of these is the one we're going to choose. We're going to choose the one in which liters cancels out and we end up with our target, which is gallons. So I'm going to choose this second ratio here because it has liters on the bottom, and liters divided into liters cancels out liters, which I want to happen. And I want to be left with gallons as the unit of my answer. So I'm going to put 1 gallons in the numerator, and I'm going to put 3.785 liters in the denominator. As I said, liters will cancel out, and I will end up gallons. And that's way too many significant digits. This is a multiplication, and the data going in, I have 3 sig figs in the 16.3, so I have to round off the answer here to 4.31 gallons. Okay, let's try another problem. A tourist flies to Czechoslovakia. He's got $1,000. He goes to the bank. How many Czech koruna will exchange for his $1,000? So we have 3 conversion factors. 145.46 Czech koruna equals 5.56 euros. 0.78 euros equals 0.66 British pounds. And $7.16 equals 4.70 British pounds. So how would we do this? What I want you to do is pause your playback, you try and do it, then come back to the video and we'll go over it. Okay, let's try this now. The first thing is that we want to specify the target, and our target is how many Czech koruna. So we want KC. That's what we want to end up with. We'll put that in a nice box. We're starting out with $1,000. So what's our first step? We look at the conversion factors we have, and we see that we can go from dollars to British pounds. Our first step, how many British pounds, is going to be equal to that $1,000. So we set up our ratio of dollars to British pounds this way, with dollars in the denominator and with pounds in the numerator. We do it this way so that dollars will cancel out and we'll be left with British pounds. So now we have 656 British pounds. What's our next step? We look over our conversion factors. British pounds we can convert into euros. So how is that going to look? We take our 656 British pounds and we use a ratio between euros and British pounds, putting euros on top, British pounds on the bottom, so pounds again cancel out, leaving our answer in euros, and now we have 776 euros. And what would be the next step? Of course, that would be now converting the euros. 5.56 euros equals 145.46 Czech koruna. So how is that going to look, and how many Czech koruna will exchange then for the $1,000? Well, we take our 776 euros. Now we multiply by a ratio of Czech koruna to euros, putting euros in the denominator, so euros cancel out, and leaves us with an answer in Czech koruna. So here are some metric prefixes to memorize. Nano means times 10 to the minus 9, or a billionth, really. So if you have 556 nanograms, that would be 556 times 10 to the minus 9 grams. Nanogram means a billionth, or times 10 to the minus 9. Micro, or a millionth, is times 10 to the minus 6. Milli, or a thousandth, is times 10 to the minus 3. Centa, times 10 to the minus 2, or a hundredth. Getting larger prefixes, kilo is 1,000 times 10 to the third. Mega is a millionth times 10 to the 6. And giga is a billion times 10 to the 9. You need to memorize each one of these prefixes so that if you see them, you can put the correct exponent of 10 in front of the number. Conversions between the English system and the metric system are going to be provided to you, so you do not need to memorize these. 1 kilometer is 0.62 miles, etc. All of these will be provided on a data sheet at the back of any quiz or test. We would also provide you the relationship or the equation to convert Celsius into Fahrenheit. Now you might not get both of these, you'll get one of them. So if I give you this one, degrees C equals degrees F minus 32 divided by 1.8, you ought to be able to solve for degrees Fahrenheit. I shouldn't need to give you both of them. Or if I give you this one, you should be able to determine degrees Celsius. That's just simple algebra, and we expect you to know that, of course. So Fresno recently hit a temperature of 112 Fahrenheit. What was that in degrees C? Plugging into the equation, degrees C equals Fahrenheit minus 32 divided by 1.8, which is 44.4 degrees Celsius. Here's another one. Sometimes in a problem you need to do a little calculation before you get to the actual conversions. A force creates a pressure of 92.6 kilopascal on a square surface 2 foot on a side. How many pounds is this force creating on this surface? And we have pounds per square inch equals kilopascals, a conversion. First of all, let's identify what the target is. We're interested in a unit of pounds. So that's our target, that's our goal, and that's our guidepost. That's where we want to end up. Now, if you look at the conversion factors we have, we see 14.69 pounds per square inch is equal to 101.3 kilopascal. If we are able to figure out how many pounds per square inch we have from this value of kilopascals, that'll give us the force in pounds per square inch. And if we know the area in square inches, we can then multiply the pounds per square inch by square inches to get the answer. So that's how you would think through this problem. Let's go ahead and do each one of the steps now. First, we're going to convert to pounds per square inch. We're given 92.6 kilopascal. If I multiply that by the ratio in which kilopascal is in the denominator and pounds per square inch is in the numerator, we will cancel kilopascals and we'll end up with 13.43 pounds per square inch. So that's our first step. We know that this square surface is 2 feet on a side. So 2 feet times 2 feet is 4 square feet. And we also know that there's 12 inches in 1 foot. So if I square this relationship, I would have to square both the 12 inches and 1 foot to get an equivalence between them in square feet to square inches. So that would look like this. I square both the 12 inches and I square the 1 foot, and I end up with 144 square inches is equal to 1 square foot. That's an equivalence. I had to calculate that equivalence for myself, that conversion factor. The big mistake students make on a question like this is that they fail to square the 12. They'll square the units, but they won't square the number for some reason. So once you know this equivalence, then it's easy to go from square feet to square inches. You just apply the ratio, cancel out square feet, end up with 576 square inches. Finally, you can take the 576 square inches and multiply it by 13.43 pounds per square inch, what you came up with in your very first step, and you end up with 7.74 times 10 to the third pounds. And that's how you do that problem. Okay, a small cube of aluminum measures 0.614 inches on a side. It weighs 0.3616 ounces. And I want you to find the density of aluminum in grams per cubic centimeter. So what I'd like you to do is pause the playback and try and get this on your own, and then come back and we'll go through it. Okay. So in the ChemRap session, the first line was to identify the units of the answer. And since we're trying to find density, the units of the answer is grams per cubic centimeter. That's very important to identify that because it gives us a roadmap on how to solve the problem. For example, here you have cubic centimeters as part of the units, but the dimensions of the cube are in inches, 6.14 times 10 to the minus 1 inches on a side. So it seems to me our first step is to convert inches into centimeters, and then since it is a cube that number of centimeters to get cubic centimeters. And now we have the volume of the cube, which would be in the denominator. So how would that look? Well, unless we go elsewhere to get a conversion factor between centimeters and inches, we probably will end up using the conversion factor given to us in this problem, 24 millimeters equals 1 inch. So we will use this conversion factor, and then it'll be very simple to convert millimeters into centimeters. So we have 0.614 inches, 1 inch on the bottom, so inches will cancel out, 25.4 millimeters in the numerator. When we multiply, inches cancel, and we're left with 15.6 millimeters. But that's still not centimeters. So we take our 15.6 millimeters. 1 centimeter is 10 millimeters, so we divide by 10, we get 1.56 centimeters, and then we cube the 1.56 to get the volume of the cube, and we end up with 3.80 cubic centimeters. So now we have the denominator of the problem, 3.80 cubic centimeters. Okay, the numerator is in grams on our target units, but we're starting with ounces. So it also seems to me we're going to have to convert these ounces into grams. And we are given the direct conversion factor, 28.35 grams equals 1 ounce. So using our conversion factor, we put ounces in the denominator, so ounces cancels out. We're left with grams. When we multiply it out, we have 10.25 grams as the mass. So now we know both the mass of the substance in grams and the volume in cubic centimeters. Divide one by the other, and we end up with this, 10.25 grams divided by 3.80 cubic centimeters gives us 2.70 grams per cubic centimeter. So we've talked about accuracy and precision, but we've never gotten around to defining these terms. Well, accuracy is how close a measured value is to the actual or true value. Or if you have a series of measurements, then the average of those measurements would be close to the measured value. Precision is how close in value all of those measurements are to each other. So you're taking several measurements and they're all very similar. That's high precision. It may not be high accuracy. Now, to discuss this, I use the analogy of a dartboard where the center of the dartboard, right here, is the true value. And the darts are individual measurements. So let's say we have a situation where all of our darts are close together, but not near the bullseye. What is that? High precision, low accuracy, high precision, high accuracy, low precision, low accuracy, low precision, high accuracy. Well, the darts are all very close together, so that would be high precision, but it would also be low accuracy because their average is not near the bullseye, right? All right, so how about this situation? What do you think this is going to work out to be? Which one of these options? Well, let's see. The precision is all over the map, but they seem to be canceling out each other so that if we get the average of this, we're going to be right smack in the middle. So this is going to have terrible precision but high accuracy. We call this kind of result lucky. This is lucky. Generally, you don't have terrible precision and then high accuracy. All right, how about this one? I think we'd have to call this one low precision and low accuracy. Well, you get the general idea of how accuracy and precision work. Your book has a section on spontaneous processes that is important for you to read and understand, since we'll be talking about the terms potential energy and kinetic energy quite a bit. Potential energy is the energy due to the position of an object or its chemical composition, and it is inherent in the compound by virtue of its position compared to that of other objects. Kinetic energy, on the other hand, is the energy due to the motion of an object. So potential energy, like this weight on top of a roof, that weight has a high potential energy. You push it off the roof and now there's a tremendous amount of kinetic energy as the weight drops. And when the object finally hits, that kinetic energy is converted into heat energy. So All forms of energy are interconvertible. Energy is neither created nor destroyed. When a process results in materials with less potential energy at the end than there was at the beginning, the difference in energy is released into the environment.